Cool. So today is like the last of our little case study discussions, and trying to like kind of go into cool, recent areas that have been interesting on the, robotic control front. So last time we talked a bunch about walking and kind of how the control stacks look for modern quadrupeds, basically. Which again is one of the really hot areas of the last few years. So today, kind of to wrap things up, to talk just about another area that's super hot that again, like probably many of you will go work in after this, is driving. So sort of the slightly tongue-in-cheek version of the lecture title is How to Drive a Car. And then as a kind of bonus top, so we'll go a little bit about like what these things look like, how they work, and then a little sort of more researchy flavored thing out of our lab, which is game theoretic MPC, which is recent research stuff from the last couple of years from our group on how to reason about multi-agent, multi-driver kind of interactions in sort of more sophisticated ways than is currently standard in autonomous driving stacks, which is kind of interesting. So I'll show you some of that. So that's kind of what we're going to talk about. So first off, like a little historical perspective then. Autonomous driving dates back a lot farther than, like most of these things, right? It goes back a lot farther than you might think. So the first primitive demos of autonomous vehicles actually go back to the 1920s and 30s, which is kind of nuts. There were a bunch of demos where they would like embed various like kind of rails or things in the road surface to follow and basically do line following in very simple like electromechanical ways. But there were kind of like all kinds of demos built around towns or cities where there'd be a few streets with these kind of things embedded in them, and they could get cars to drive around, autonomously in various ways. So these ideas have been around a long time. And then I would say the first kind of like a lot of this stuff, the first serious modern work, like if you look backwards from where we are now on this stuff and try to trace back to like a common origin, I would say the first recognizably modern work that you could trace a line to today is from the 80s. And there were essentially two groups doing it back then that were getting real serious. One was at CMU, and you could really call CMU the birthplace of modern autonomous driving in many respects. And then there were also some groups in Germany, kind of at a couple of universities, and also kind of funded by and done in cooperation with Mercedes-Benz. So basically CMU and sort of a group in Germany doing this stuff in the 80s. That got pretty serious. And then sort of in the 90s, there were lots of fairly impressive demos. There was actually a cross-country, across the US coast-to-coast road trip that was done like 95% autonomously in the early 90s by some people from CMU, which was at the time like a minivan with the whole back full of racks of computers and cameras and all the usual stuff. But like it was pretty good back then, right? Like for highway, they got 95% of the mileage coast to coast driven autonomously, with like 5% where the human driver had to take over. So I think this is a classic long tail problem, right? Like we were at 95% in say 1995, and like in 30 years, we've chased down that last 5%. So now we're probably, a few percent better. Maybe like if you tried to drive coast to coast with like a Tesla full self-driving sort of thing now, I don't know, you'd probably be, I guess you'd do 99% or so, but you still have to take over occasionally, right? So I wonder where we'd be at today, but it's kind of interesting, like, how far it was along 30 years ago versus where it is now. So yeah, there were demos, CMU demos back then. There were also a bunch of demos, similar demos in Germany, and they sort of both got around this 95% autonomy miles kind of metric. Most of this is pretty much all highway driving also, right? Which is sort of similar to today. That's the stuff we're pretty good at. And the urban stuff is super hard still. And then kind of from there was the, I don't know how many of you guys were around for this, but I was an undergrad when the DARPA challenge stuff happened in the early 2000s, and this was a huge deal. And that really kicked this stuff forward in a major way, right? So that really, and then like literally the top few teams from that DARPA challenge were basically, a bunch of them ended up being like the founders of a bunch of the autonomous driving companies, right? Like they literally just spun out of those teams. Like the Stanford team became Waymo, for example, and like a handful of the other ones, essentially you can trace like several of the current companies back directly to a couple of those DARPA Grand Challenge teams. Okay, cool. So that's that. So then like kind of similar to what we did last time, kind of a big picture of sort of the full stack for this sort of stuff. So let's draw a big block diagram. So there's sort of perception stuff. Then there's sort of a couple different things from here. So there's a path planner. And then sort of on top of that, there's also this like what we'll call high level planner. Which is like your kind of Google Maps level routing kind of stuff. This path planner then goes into an MPC controller that we'll talk some more about. And then there's generally some like low level actuator type controllers, but more or less it goes from there to the car. And then we have, our typical feedback loop situation. There's some sensors. And that's kind of what these things look like. On the sensor side of things, typical, cars, everyone's got GPS, everyone's got IMUs. Then from there, it varies quite a bit. So, most of these have some combination of cameras, LiDAR, and radar in various combinations and configurations, depending on the car and et cetera, right? If you're Tesla and Elon, maybe just cameras. Most of the other car companies are doing more. The one thing that has been really interesting in the last few years watching this space is how autonomous driving has has really pushed the development of these sensors. You can now buy an automotive grade radar for like less than $50. Like radars are so cheap now. I really want to do more things with these because they're so cheap. It's like really enticing. Like you can buy these and there's like SDKs for them. They're so easy to use now for like $25 on DigiKey. Like there's probably other uses for these. So that's the sensor part. And then I would say at a high level here, like as a controls person, I would say of this whole thing, the perception part is really the hard part. Like as a control problem, driving a car is not super difficult. There are definitely some edge case things that are hard, and I'll show you some of that. But, throw MPC on here, it's going to work reasonably well. The dynamics are pretty easy to model. It's pretty forgiving. The real challenges come in to like, basically perceiving other cars, perceiving pedestrians, bikes. There's just like so many weird edge case phenomena that can happen. Especially in urban settings, right? That this becomes really hard. Add weather to the mix and like crazy lighting conditions, it gets to be ridiculously hard. And if you're being honest, right? If we're being honest with ourselves, like when we drive, there are scenarios where we're driving where you can't really see what's going on, right? Like lots of glare, dirty windshield, rain, like crazy. There's scenarios, fog, whatever, where we're driving with like pretty subpar perception, right? And it's, if you think about trying to do that autonomously, it gets like, just imagine how hard this gets, right? That, again, classic long tail problem. So that's really the hard stuff. So then just kind of going through the blocks, that's the perception stuff. This high level planner thing. This is, route planning. This is the sort of thing that, Google Maps does. And this is generally done with graph search. And this sort of generates waypoints, right? So that's the very highest level. Then underneath that, this thing that we call the path planner. What this thing is trying to do is generate smooth, collision-free paths. So usually this is some, spline curve. And generally this, at this level, there's no dynamics involved. So this is at a very high level. It's basically in like 2D XY space, and it's taking in information about obstacles, potentially dynamic obstacles, right, from the perception stack, and it's just trying to find a smooth curve that that doesn't hit anything, right? And there's typically, right, you can imagine if I'm just doing a spline curve, sort of baked into this are sort of curvature limits and things like this that sort of implicitly, in a conservative way, bound the accelerations on the vehicle. So the idea is if I set up the splines the right way and put a handful of high-level constraints on the spline curves, I can make sure they're not too wiggly or whatever, and therefore I should be able to track them with the actual car. Right? So you can think of this as like, these are typically set up in a pretty conservative way so that you can limit the acceleration along the curve such that you're pretty sure the real car can track this. And for most driving scenarios, i.e. like not aggressive racing, this is what you want, right? You want stuff that's smooth and like gentle and not like overly aggressive acceleration wise. So you're not really reasoning about the car dynamics for like normal around town type of driving. Then the last thing, which is mostly what we're going to talk about, is the MPC controller. And this is, basically taking that spline curve and tracking it in real time while reasoning about the vehicle dynamics. And constraints. Okay, so yeah, and this is what we're going to mostly talk about, since it's the part that most closely relates to the class. So now, like some quick discussion of like vehicle dynamics models. These are surprisingly dumb, and you can get away with really, really simple models. Again, for like most benign driving conditions, like 90+% of driving that we would actually care about, like on the highway, around town, whatever, you're not really ever pushing the vehicle limits, right? You're not really ever flooring the gas or like turning super aggressively such that you're pushing the friction limits on the tires and stuff like this. It's always pretty benign. So you can generally get away with very simple models, right? The less aggressive you're being, generally the simpler, more approximate models kind of work out. So at a high level, there's lots of options here with different levels of fidelity. The most basic one, which again, you can get away with surprisingly, often, is the kinematic bicycle model, or we'll call it the bicycle or single track model. Okay, so, and there's a few versions of this. So here's the simplest one. Kinematic bicycle model. So let's say we've got, some coordinate system for the world frame, like x, y, theta. And we've got, so you model it as two wheels. So here's like, say, one wheel, other wheel. We've got some L here, the distance between the axles. We've got, say, the velocities defined here. We've got in our world coordinate frame, we've got like our angle relative to the world here, which is our theta. And then we've also got this sort of, that's the heading angle. And then we've also got the steering angle here, which we call alpha. And then your inputs are V and alpha. You can also write this down in again, there's various flavors of this. If you wanted to account for acceleration limits and stuff like this, or turning rate limits, you could add an integrator to the dynamics and make the input alpha dot. Again, that lets you put limits on the rate at which you can turn, right? So if we assume the tires don't slip, which is, again, like assuming you're not driving super aggressively, this all holds. Then it's just kind of, if we write down the kinematics of this thing, we get something like x dot equals v cos theta, y dot equals v sine theta. This is just geometry, right? And then theta dot equals v tan alpha over L. And then you can make, the U can be either alpha or alpha dot. To account for the steering limits, we'll add alpha to the state and make it alpha dot, say U2. Then we've got our state, X, Y, theta, and alpha. And then our controls would be V and alpha dot. So you could also imagine, right, if I wanted, so this assumes that I can instantaneously change velocity, which is obviously not true, right? What I really get access to is acceleration or throttle. So similarly, I could add an integrator to the velocities and get an input that's really like torque, right? And integrate that up. And that would be then allow me to reason about throttle and braking limits, as well as these steering rate limits, right? And so that would be, if I do that, that's called the dynamic bicycle model. This is called the kinematic bicycle model because, again, I'm just integrating the kinematics and I'm assuming like instantaneous control over the velocities, right? Cool. Any questions about that? It's like, if you sit there and do a little trig, you can kind of get this stuff. It's not too hard. And this sort of setup works reasonably well for normal driving. And you can do all kinds of fun things. If you stick this into like ILQR, say, you can get it to parallel park pretty easily and stuff like that comes out, which is fun. But this is going to break down if you do more aggressive stuff, right? So if you're pushing the actuator, like if you're, flooring it, if you're trying to change that V super quickly, here I got instant control over V. In real life, I don't. And I have limits on how fast I can accelerate, either with the throttle or with the brakes and stuff like that. So this totally doesn't reason about that. And so if you try to push this hard and do very aggressive things, it's going to break down and it's not going to be a good model anymore. That high acceleration, basically. And also, right, the other thing this is missing is any notion of friction limits for the tires, right? So again, if you're cornering hard, all that stuff, this is going to break down. So stuff you can do from here, sort of more complex models and what they typically include. The first one we kind of already said is this so-called dynamic bicycle model, where you include the accelerations as well. So basically here, you'll model the car as a rigid body. And actually integrate all the forces up. So kind of have F equals ma. And in 2D, we have just tau equals j omega dot. And then this lets you reason about things like engine torque, tire forces, braking, etc., sort of explicitly. And obviously, this can reason about more dynamic behaviors and kind of pushing the limits a little bit more. And basically, short of like absolutely flat out like racing on a track against like pro level drivers, this is basically anything you want to do with a car on the road. This is pretty much good enough. Again, it misses some of the most crazy stuff. So like if you're cornering, for example, if you're racing, cornering super hard, you're loading different sides of the car, more than the opposite, right? So like if I'm cornering around the centrifugal force from cornering is going to load the outside wheels more than the inside wheels. So I have more friction capability on the outside tires, blah, blah, blah. Stuff like this is missing from the single track model. But again, this is only going to show up when you're really, really pushing the vehicle really hard. And this is pretty much going to cover any on-road setting, just shy of like, again, like really serious racing behaviors. So to get to that, you start thinking about the sort of what's called the double track model. So here you've actually got both sets of tires, like you model explicitly, all four wheels. And you can now think about the full 3D rigid body dynamics. So now you can think about like the suspension dynamics, body lean, all this other stuff, right? Body roll, weight transfer between the tires. And then this really where this starts to come up is super aggressive stuff. So like racing or drifting, which we'll see in a sec. Or the other place where this really starts to be necessary is off-road driving, where you're not on the road, where you have to think about terrain, right? And how that interacts with each tire individually and how it interacts with the suspension. Okay. And then last, there's a lot of literature on tire models, which if anyone's done any driving, you've probably heard of these like crazy, the magic tire model and like all this stuff. There's some really kind of next level, very complicated things people have done in this area. So, they can go from simple, where if you're doing, again, really benign stuff, you just assume you're not slipping, to sort of, I would say, medium complexity, where you might assume like a Coulomb model, like we've talked about for walking, right? Coulomb friction, stick slip, to extremely complicated. So there's lots of these where you reason about things like the actual contact patch of the tire, tire deformation, and like all kinds of nonlinear stiffness effects and stuff. So it gets really complicated. People spent a surprising amount of effort like modeling these in great detail. Okay, so having said that, if you're driving on the road, pretty much that dynamic bicycle model, is all you need, I would say, in almost all settings. I will show you some examples of this now that are super fun. Okay, so maybe some of you guys have seen this stuff. This is from Chris Gerdy's lab at Stanford. So they did autonomous drifting from 2019. So yeah, pretty awesome. They like drove around and did figure eights and stuff in this DeLorean. So the paper for that, I'll show you the paper in a sec, but yeah, so this is awesome, obviously, and really kind of super aggressive, pushing the limits of what you can do. And it turns out this is like vanilla MPC with a dynamic bicycle model. So it's still a single track model with like a pretty sophisticated tire modeling setup with some like low level feedback on the tire slip stuff that they kind of hacked together. But yeah, the results are insane. So this paper, if you want to check this out, yeah, so they have this paper, they kind of go into, again, it's single track model that we just wrote down, basically with some more sophisticated tire modeling to actually reason about like the friction stuff. So again, you go surprisingly far with these like very simple cartoony models, right? So that's nuts. And then just generally what that group's all about is autonomous racing. So they have this like Audi TT that they take out on the track and try to get, they do time trialing. They try to get really fast times around the track. It's, if you actually turn the audio on, there's lots of tire squealing. It's super aggressive, cornering and stuff. And they actually compare against expert human drivers. So apparently at this point, they're at the level of like a really, really good amateur driver. So they can beat most like weekend warrior amateur drivers. They're still not as good as a pro like Formula One driver or Indy driver, which is kind of interesting. So anyone have any thoughts on why, like where the gap is? So this thing, it's doing MPC. They've got like a model of the track. They've got GPS. They have like tons of good knowledge of what's going on. Yeah. So no, this is just time trialing. There's nobody else on the track, right? It's just go around the track as fast as you can, get the best lap time. They don't have to worry about other drivers, none of that, right? And so if they do it and then they're racing against the clock, right? So they do a lap. If you take an expert level human, so if you take like a weekend warrior amateur and let them in the same car, right, do a lap, it's competitive against that sort of driver, but against a pro like F1 or NASCAR driver, it's not. Like those guys still beat it.
Is there dynamics missing on the curves that the NASCAR driver can take advantage of, but this car can't reason about them?
Not really. So they can throw tons of dynamics at this. Like you can have a fairly sophisticated dynamics model.
But it's still not.
Yeah, but there's like a couple of places that are really actually.
To go as fast as you can with a car, you got to be like just in the very edge of like slipping with all four tires.
Yeah.
And like getting that car to do it is extremely hard. And
yes.
They're pretty much four-wheel drifting as they're going.
So it's, yeah, you're starting to get at it. Yeah. Did you have thoughts to add to this?
Yeah, like the ideal grip level is at like a 1.1-ish slip level, like slip ratio.
Yeah, so it turns out basically, so they've compared against data from human pro race drivers in these kind of settings. They've recorded actually really next level data of like eye tracking and trying to figure out what the humans are doing. And it turns out what's happening, if you compare the autonomous controller to the human, there's a couple of things that pop out in really interesting ways. And it's a classic like exploration versus exploitation trade-off. So essentially what's going on here is, like you said, the optimal thing to do here, when you're cornering, for example, you want to take those as fast as you can. So the optimal thing to do is push right up to the tire friction limits, but not exceed them, right? Like you get the most grip just shy of slipping. When you slip, you get less grip, right? The problem is over time, as you go around the track, as the temperature changes, as the tires heat up, as the track gets more, gunk on it, the friction coefficient changes dynamically as you drive. It actually changes like lap to lap. It changes around the track in different spots. And managing the friction limits is actually the most important thing when you get to this level. And in the MPC controller, they basically like set a number there for the friction coefficient, and that's it, right? If you look at the data from a human driver, what they're doing is constantly pushing just past the friction limits and slipping a little bit. So if you watch the MPC controller go around the track, it basically never slips. It goes right up to its fixed limit that you put in there, but it doesn't go past it ever. The human driver is constantly slipping a little bit here and there around the track, probing the limit. And if you actually talk to pro level drivers, they actually build up a mental map of friction around the track. And they're doing things like listening to audio cues and like feeling in the steering right up against that edge. So they listen for tire squeal, all these things, and actually like are dynamically exploring the friction limit and keeping track of what it is in different places on the track dynamically and updating that mental model as they go. And that's kind of the main difference, is that the human driver is constantly probing for these friction limits and going just up to them or just past them, actually exceeding them a little bit, because there's no way to know where it is until you exceed it. So if you think about it as a purely deterministic problem, that's suboptimal, right? Because you get less grip when you exceed it. But in this scenario where it's actually a stochastic problem with uncertainty and stuff, it turns out the humans basically has an exploration sort of thing going on where they're doing something that if you had perfect knowledge would be suboptimal, right? But in this sort of not totally deterministic setting, this probing behavior it turns out is necessary, right? To really tease out what's going on. So this is super interesting, I think, personally, and like gets at one of the most classic trade-offs in like stochastic control. And like right now, the MPC controller is not doing that. It's purely deterministic. It's assuming a fixed friction constant. You can imagine like writing an estimator that did this online, that was trying to update, that had a map of the track and was trying to map out the friction coefficient online by doing this kind of stuff. They don't do that right now, right? And that's basically, I would say, the main thing that separates this from a pro level Formula One driver. Yeah.
Also not really observable unless you flip anyway.
That's exactly right. So that gets at this, again, really classic exploration exploitation. You're actually, if you had an oracle that told you this, like this behavior of probing and slipping is suboptimal, right? But in this setting, the only way to know is to go past the limited slip, which is suboptimal from a performance perspective, but it's the only way to know. So there's this really fascinating trade-off where the exploration makes your cost a little worse, but like you don't know without it, right?
You
And
have to like make your control policies slightly suboptimal.
yes, exactly. Yeah. So I get another way to say this, in the not perfectly observable like stochastic setting, like when we talked about LQG, we talked about the certainty equivalence thing, right? Where the optimal thing to do is just take your state out of the state estimator and just run your controller on the mean state. That's certainty equivalence thing. We talked about, we always do this pretty much in practice. That's happening here, right? But this is very much a case where certainty equivalence does not hold. Like you have to, the control policy you need in the partially observed stochastic setting is fundamentally different in this way, right? From the certainty equivalent controller. Right now, they're running a certainty equivalent controller. You have some estimate of the friction, you just go plow right ahead, assuming that you have perfect knowledge. You need a fundamentally different controller with this sort of like information gathering objective, right? Then you get in the certainty equivalent sort of scenario, right? So this is classic, as soon as you go nonlinear, this sort of stuff starts to happen, right? And it's always there. We almost always make this certainty equivalence separation principle assumption coming from LQG because it makes our lives easy. But in real life scenarios, that's suboptimal, right? And this is a really kind of nice illustration of where it starts to break. So if you're into this stuff, these guys, this is Chris Gertie's group at Stanford. They're, I would say, for this kind of really aggressive on-road driving, these guys are kind of the state of the art. So they drifting stuff. And then if you want to see kind of the more vanilla stuff, they have a lot of work on MPC on cars and like real-time, trajectory replanning and stuff like this. They've also done some work on like, nope. Maybe. So certainly there's this problem we just talked about, right? I would say you maybe could get an RL agent to do this. Right now, this is the state of the art, though. This is way better than any RL policy, but it's missing this piece, right? And I'd argue like you can get at that in like a very classical way, right? We could write down like a better state estimator for this and estimate out the friction and like get that behavior, right, in this kind of setting without going to like, you know, a policy gradient method or whatever. And I don't know, like there's two ways of doing these things, right? You could,
In RC cars, I've seen like people driving it with remote control and then the car is mimicking that behavior.
oh yeah, for sure. You can get that behavior. Yeah, you can get it a bunch of ways. You don't necessarily need to do deep RL to do it, right? And this, right, like people have done RL for driving. This is still way better than like anyone's RL policy that I'm aware of. But yeah, these behaviors, again, like they're these really basic things that come out of like stochastic control and nonlinear control in general, right? It shows up here. You can get at it like RL, you know, can get at this sort of stuff, but you can here as well. You just think a little bit, right? And like build a model and you know, kind of reason through these things. Yeah. Anyway, super fun. These guys are awesome. And yeah, cool stuff. But this kind of so this stuff too, it's sort of stuff we're talking about and, you know, thinking about friction limits and stuff on the tires. But actually they're doing pretty much exactly the stuff that we've talked about in class. It turns out, so that second paper in particular, I was on that guy's thesis committee, so I have a pretty good idea of what's in there and what they're doing. Essentially, the state of the art there, which again is very aggressive driving, right? Way crazier than you would see on a normal car, right? And that's using these dynamic bicycle models with maybe, you know, slightly more sophisticated tire friction models. And essentially what they're doing, what's on those cars that I just shared you, like both the track stuff and the drifting stuff, they're using a dynamic bicycle model. With, you know, more sophisticated, maybe tire models. Right, in both those examples, that's what they're doing. And then they're literally doing online MPC with IP-opt on the cars. They're running IP-opt in that control loop at like 50 hertz, doing nonlinear MPC. And yeah, 50 hertz is fast enough, it turns out, for like almost all these driving things. You get reasonable horizons and really good performance, like you saw. There's a lot of tricks in hand tuning. And so it's nonlinear. It's definitely a non-convex problem. And that's kind of scary, right? And we've said, you know, you can't guarantee convergence and stuff like this. So practically what they do is they tune this up, they play with the cost functions and stuff, and like a lot of Monte Carlo, right, to make sure it's going to converge like as best you can in an engineering sense. And then they go run it on the cars, and they basically have a time budget for the solver, you know, say like 20 milliseconds or whatever, right? And if it doesn't return a solution in that time window, they have a fallback where they either, you know, keep running based on the last one, or if it takes long enough, they will switch over to some like safety controller that's doing some more simple like PID thing that basically can safely bring the car to a stop. But practically speaking, it basically never fails. Like they do all these examples and never have any problems with it. So that's kind of interesting. It seems sketchy, but you know, we're doing it. Cool. So any questions about that stuff? Super fun. Okay, cool. So that's you know how most of these things work. I'd say like it's hard to say what the industry stuff's doing, but I'm, you know, with fairly high confidence, like most of them are doing similar things, right? Some kind of bicycle model, some like pretty basic nonlinear MPC, again, gets you really far, and you can tune that so it's pretty reliable. Okay, cool. So then switching gears to like interesting researchy things, just as a nice little hint of like some cool problems if you're into this kind of stuff. This is a, you know, kind of a big deal thing. The frozen robot problem. Who's heard of this? Anyone? Okay, like not many people. So do you want to give a quick like summary of what this is about?
Hopefully I will I think it's pretty much about getting stuff, right?
Yeah.
It's processing that and we'll go over that or something. take it out.
Yeah, so it typically shows up. So it shows up in driving for sure. It also shows up in more general, like navigating crowds around people kind of scenarios on mobile robots.
There's a lot of too close to the dam.
Yeah,
That's
exactly.
your conservative limit.
Right. Yeah, exactly. So the gist is like the easiest example to talk about maybe is for like for highway driving. If I'm like trying to merge onto the highway and there's a lot of traffic, and say so I'm coming down the ramp and there's like dense traffic with all the cars bumper to bumper at the bottom of the ramp. What most autonomy stacks will do right now, they'll get to the bottom of the ramp, they'll see that there's no car-sized holes that are collision free, and it'll just slam on the brakes at the bottom of the ramp and sit there and say, I can't merge into traffic, there's no collision free path for me, and that's it. Frozen robot. It's just going to sit there forever and never like do anything. So what we would do, right, as human drivers, is reason about, hey, there's no space right now, but none of these other drivers want to hit me. And so if I like kind of slowly nudge my way in there, they're going to make space and I will be able to merge in, right? That's what the human driver does, right? So was that
That's
probably maybe, but this is a reasonable prior assumption on like the behavior of other human drivers, right? That they don't want to hit me any more than I want to hit them. They're going to try not to collide. And if I kind of nose in whatever space there is, the other driver behind is going to probably have to sit there and make room, right? And I'll be able to merge. So that's what we do. But at the core of that, if you think about what's going on, it's this coupled reasoning about what I'm basically doing is assuming some things about the other drivers. Basically, if we're thinking in control terms, I'm making assumptions about the other driver's control policy, right? And the fact that they have some collision avoidance, objective or whatever constraints. And if I kind of push in there, I can take advantage of their collision avoidance behavior. And like, there's this coupling though between your control decisions and theirs. And you're essentially assuming a certain controller on the other driver's part and like, reasoning about the cross coupling, how your actions can impact the other driver, right? So there's this like really interesting interplay that's kind of this fundamental multi-agent flavor that's really interesting and gets at the heart of some of the hardest problems in like kind of mixed autonomy around humans, right? Yes. Yeah, that's where we're going. Cool. So we're going to talk about game theory. Okay, cool. So basically, we want the MPC controller to reason about coupled behavior with other drivers. Like sort of the, if I do this, the other car will probably do that kind of thing, right? And I'd say, current system, so there's many ways you could go at this, and you could argue, about whether this is really a perception problem or really a control problem or whatever. It's kind of, there's some ambiguity there. And there's different ways to look at this for sure. And I'd say the way most current systems work, this is why another reason why the highway driving stuff is easy and why so many of these things kind of work reasonably well on the highway. A major assumption in a lot of these things right now is that other cars will continue driving at constant velocity over the MPC horizon. So, this is pretty reasonable for highway driving though, right? You look around and you see all these other cars driving in straight lines, staying in their lanes, right? And if your MPC planning horizon is only a few seconds into the future, that's pretty reasonable. And you're thinking about, I just don't want to hit anybody. So you basically roll out the, continue driving in a straight line assumption around for the next 5 seconds, say over this planning horizon, and just don't hit anything. And if you kind of do that dynamically at 50 Hertz, even if they deviate from that a little bit, works reasonably well. The thing that's missing is this kind of cross-coupled behavior stuff where, this is the, if I'm doing this in the merging scenario, I'm assuming everyone's going to keep driving and there's no gaps. There's nothing in there to reason about, well, if I nose in, they're going to make room and not want to hit me, right? That's missing from this setup. Okay, so works well for highway driving. breaks down in scenarios where you have sort of like tighter coupling. So like the ramp merging. Yeah. Okay, so now we're going to talk about game theory. So this stuff's super interesting. And game theory has like long, deep connections to optimal control, right? It's a very similar set of ideas with a lot of overlap. Oops. So let's talk about game theoretic trajectory optimization, or by extension MPC, right? Which is kind of some stuff we've done. So who's like checked out game theory before? Anybody? A little bit. So not too many people. Okay. So you've heard of this, right? At least. Okay. So here's kind of the high level idea then. What you're going to do, so we'll stick with the driving scenario, but obviously this is more general. But I'll like ground it in that language since we're talking about driving. That's a nice and concrete example. So what we're going to do here to get this like game theoretic setup, the basic idea is we're going to assume that, so we're solving our optimal control problem, right? We have collision constraints, we have some cost function, we're trying to minimize whatever. We're going to assume that all the other cars are also solving an optimal control problem. Doesn't have to be the exact same one as us, but we're assuming that they're also optimizing some cost function, maybe have some constraints, collision constraints, whatever, right? So that's kind of the first thing. We're assuming everyone is acting like solving an optimal control problem, right? In the language of game theory, this is known as acting rationally, which is a very funny way of putting this. And yeah, that's actually maybe a good way of putting this. It's like, so where this all comes from, right? Originally is economics. Like this is we'll get into it. But there, right, like this is called acting rationally, like everyone's trying to maximize profit or whatever, right? And you get this similar sort of idea. The problem is humans don't usually act rationally. That's where this is a problem. Right. Well, also in driving. quite obvious. Refer back to my morning incident of, you know. So there's kind of a couple key assumptions. One, everyone's acting rationally or optimally, right? Solving this optimal control problem. And two, we're kind of assuming to make this work, you have to assume you know it. You know their cost function and constraints and whatever, which is a big assumption. And like in general, we're gonna have to like assume even if you go to like a stochastic setting or whatever, partially observed setting, you're gonna, just to make any progress, you're gonna have to make some strong assumptions about their problem, right? Because it's not very observable in like the short amount of time you interact with someone on the road. You can't tease out that much, right? And I'd argue this is what we do when we're doing this, right? We're making pretty strong assumptions about what other people are going to do. You might update that assumption if you see someone driving like super fast or weaving, oh, they're driving super aggressively or whatever, and you might kind of bake that into your new assumptions about what they're going to do. But generally speaking, we're also making like we have strong priors on people's, behavior. So basically we do this, we assume everybody's doing this, and then we're going to solve a big joint optimization problem. With everybody's stuff all together stacked up. But it has a very particular flavor. And this gets at the heart of like, when we say this game theoretic thing, there's different versions of this, but it's not a minimum. So we're not actually, if I were to just stack up all the cars, states, and controls and like solve one big joint problem, which you can do, like, and if I were sort of controlling all the cars and say optimizing, like if I were, God, and I were trying to like optimally route traffic in a city or something and get everyone to their goal, minimizing fuel and as fast as possible or whatever, I would stack this all up in one giant thing and minimize the global cost for everybody and whatever, and like the world would be a better place, right? But that's not the scenario, right? So that would be a cooperative, multi-agent setting, right? Where everyone's talking to each other and there's some, godlike figure pulling the strings on everyone or whatever, and we're solving this giant global optimization problem, right? So that's cooperative. This is non-cooperative. It doesn't necessarily mean adversarial. It could be or not. It just means that everyone's not cooperating, not talking to each other, and everyone's kind of doing their thing on their own. There's coupling, right? But we don't all love each other, and we're not trying to necessarily help each other out, right? That's kind of the setting here. So there's different notions of solutions to these problems in general. These are called game theoretic equilibria. And one version of this, that's sort of the one we're going to talk about, is a Nash equilibrium. And this very much comes from economics, Nash game, right? Beautiful mind, John Nash, blah, blah, blah. So this is a very like natural idea when you think about it a little bit. So what we're going to do is define like this big state vector, x bar, that has all the individual ones stacked. And I'll write these like this. So this is each car. Say we have n cars. And then we'll do the same thing for the controls. We'll have a u bar with all the controls stacked up the same way for all the cars. Okay, so now this is kind of, so that's standard, right? And so how to get at this like non-cooperative flavor when I set up the optimization problem, this is kind of the interesting part. So if we were doing cooperative stuff, I would stack all this up and just minimize with respect to the U's and get this like global optimum that's the best for everyone. But we don't live in that world, which is sad. So instead we end up with this sort of thing. So we're going to minimize, we're going to end up with a bunch of optimization problems where we have everyone's state in there, but we're only optimizing with respect to one car's control at a time. And we have that car's cost function. So these are all cross-coupled in terms of the states, right? So for example, this lets me reason about things like don't follow too close to the other drivers, right? So everyone's states are in there. Everyone can see, we're also here assuming perfect observations, right? We're assuming everyone knows everything, like can see the other cars, right? So that's why, car one's cost function can depend on the state of cars 2, 3, 4, et cetera. Like I'm looking at them, watching them, I'm inferring their state, and I don't want to hit them, for example, right? So that's what's going on there. But, car one might have a different cost function from car two, right? Like car one might be a very safe, conservative driver, might not follow too closely, whatever, and that's encoded in that J1, whereas car two, right, might be super aggressive, drive super fast, follow super closely. And that might be, car two's cost, J2 might be different, right? Does that make sense? So these look like this. So all the cost functions can have all the other cars, but you're only instantaneously minimizing, your own cost, your own car kind of thing. And then you've got your kind of dynamics constraints, which I'll write like this. These are for everybody. These are the same for everyone, right? And then constraints, which again, depend on everybody. So these might be like collisions and dynamics. So everyone's got these, but the cost can be different for each. I mean, the cost can be anything, right? But yeah, maybe, for if you're thinking about it as a LQR type cost function, yeah, that makes sense, right? And then dynamics, collision constraint. Okay, so this is like, a problem for car I, right? Looks like this. So what we end up with then is we get one of these for each car. So we'll get n of these problems for n cars. Yeah. That's right. That's why you only have your control in there.
As a decision, it cannot be located.
You cannot. That's absolutely right.
So shouldn't it just take start by
No, because your cost depends on the other cars, right? Like I don't want to.
under
Hmm?
under the
No. This will become clear in a second. So that's for one car. As is, that's like underdetermined in some sense, right? Because it's only one car. I stack up n of these problems. So if I have 3 cars, I get 3 of these problems that I just wrote down, right? I can write down their first order necessary conditions for all 3, right? Basically set gradient for problem 1. I set the gradient with respect to U1 equal to 0, right? Like that control trajectory. For the second problem, I'd set the gradient with respect to car 2 equal to 0, et cetera, right? So I get sets of first order necessary conditions. And if I stack all those first order necessary conditions, then I get a Nash equilibrium. Those are the first order necessary conditions for a Nash equilibrium to that problem, right? The set of first order necessary conditions for each car's problem stacked up. Does that make sense? So that's what's going on. So you're assuming that all the cars are acting optimally with respect to their own controls, their own costs, right? Right? Make sense? And so you can think of these as n separate optimization problems, but they're coupled through the X bars, right? So I can't control what car 2 is going to do, but like they can see me and I can see them, right? And we're all kind of planning independently, not caring. Like we're coupled, but we're not trying to help each other out. We're all trying to do the best we can with respect to our own cost function, right? And we all have different cost functions potentially. Does that make sense? Cool. Okay. We get n of these problems that we have to solve simultaneously. That's the only way you can solve this, right? If I just look at this problem for car 1, I can take the gradient essentially with respect to U1, but I can't really solve for the whole set of states that way, right? It's like underdetermined. So I actually have to write down everyone's first order necessary conditions with respect to their own controls. And then I stack them all. And only then does this become like a well-posed problem, right? Where I can solve for all the states. That make sense? Cool. So the sort of classic like economics interpretation of this and the way they talk about it is that no player or like car, whatever agent can unilaterally improve their cost. So that's what's going on here. So like you can imagine, you can think of this as in a lot of different ways, but like the idea is that everyone's doing the best they can, and unilaterally, like as in if it's just me sitting here with my own controls, I'm doing the best I can. I can't make my life any better on my own, right? Like, so everyone's doing the best they can individually in this sort of non-cooperative way. And like, you end up in like kind of a stalemate situation. If that makes sense, right? And that's kind of the definition of a Nash equilibrium. Has anyone ever heard of other game theoretic equilibria? That's not a class of equilibria. What that is about tracing out a set of equilibria. Like you could get a Pareto front here by tweaking the cost functions. So it's the set of optima, like set of optimal costs as a function of some problem parameter, right? So if I had like 2 drivers and I were to sort of tweak a cost parameter and trace out the optimal curve as a function of that parameter, that's what that's about, right? So this Nash equilibrium thing is a kind of fundamentally at its core, like symmetric and reflects like symmetry of information and like everyone's kind of even playing field, right? Yeah. That's one of these. Yeah, that's a sort of an example of a Nash equilibrium. Yep. But there's some other ones. So this one has this like symmetry kind of flavor, right? Where everyone's kind of on equal footing, has the same information. That X bar shows up everywhere, right? So everyone can see everyone else, blah, blah, blah. There's other notions of game theoretic equilibria that are a little different in terms of like, they have like information asymmetry or like a leader follower kind of flavor. And so like another very common example of a game is a Stackelberg game. Has anyone heard of that? So that's one where you have a leader follower. So like you have player 1 goes first, player 2 follows. And there's this fundamental like ordering and asymmetry to the problem. Fun fact, I don't know. There's different versions of this. Okay, so that's that. And then, yeah, this Nash equilibrium idea is maybe, a good model of non-cooperative driving. I don't know if it is or not. Maybe it is. We kind of think so. Some other people think so. But I would say no one's done a very good like data-driven analysis of whether this is a good model or not. Like taking a bunch of human driver data and tried to like look at if the Nash thing fits it reasonably well or not. So who knows? And then, yeah, like you can imagine the cost function capture behavior, right? Yeah, I don't think so. Like we've played around with this. Some other groups have played around with this and looked at it. But yeah, I don't think anyone's like sat down and like taken like a data set of like human driving data, like trajectories that have been observed, in the world, and then like tried to fit a Nash equilibrium to it and looked at like goodness of fit kind of stuff, right? So I don't think anyone's empirically verified that like the Nash equilibrium model is a good model of like human driving behavior in particular. And the economics literature for the last like say 20 years or so has really kind of poked at this assumption because it's based on this rationality assumption, right? That humans are optimizing, right? In economics, it's like optimizing for profit or whatever, right? And like all the recent research in economics has basically poked holes in this assumption and like shown that humans at their core like aren't that rational and like act suboptimally all the time. And like maybe this isn't the best model for an economy, right? So probably that also holds true in driving. And we can all come up with many examples of people being stupid, bad drivers. So like, I think that probably is also true here. So there's a question of like, how good of an assumption is this? And like, is this reasonable? And I don't know. But I think that, like I would love to see a study or do a study where we take like a big data set of human driver behavior and actually try to back out, does it fit a Nash equilibrium assumption, right? I think that'd be interesting. I don't know. I don't think anyone's done that.
What other models exist in the for that?
So I know there's some of this stuff in the economics literature, and I like frankly just don't like follow that stuff super well. I know that this is a thing, and that's kind of the origin of a lot of this stuff, and that like they've gone away from this in like recent decades and have started to look at like various irrational flavored things. But yeah, again, I'm not super up to date on that stuff. Yeah, I don't know. It gets weird. So yeah, cool. Oh, what else? Okay, cool. So let's see. So then this is a thing you can maybe model this as Nash equilibria. Maybe that's reasonable. I'd say what the saving grace is in the driving scenario, though, if you do this, I'll talk about how we do this, and then but really at the end of the day, like as with lots and lots of examples of model-based control, MPC, et cetera, we get away with cartoonishly simple models, right? In a lot of cases, linear models all day, if we can get away with it with MPC. So even if this is a pretty naive model of human behavior, it still captures the essence, right, in a nice way, similar to how we might get away with some really dumb linear, like the potato model for a quadruped, right? It's a ridiculously oversimplified model, but it works in a lot of cases, right? I think a similar thing kind of here, right? We use this very cartoony model, but we run it really fast online in the loop, and we are constantly adapting and doing feedback. And as long as it captures the essential flavor at a kind of like basic qualitative level, the thing that this does for you, like this is, if you think about it as like, a lot of cases, the linear model, as long as it gets the sign on the gradient right, is going to stabilize your system and you'll do okay, right? Here, I think it's a similar thing. Like this captures the fundamental basic qualitative fact that there's this cross-coupling interaction among drivers, right? So maybe in that sense, like, again, it's good enough. It points you in the right direction, in terms of the gradient or whatever, and like gets you qualitatively the right kind of stuff. And then if you do feedback on that, that kind of mops up a lot of the errors and the messiness in the world, right, compared to your model. So I don't know, but philosophically, I think I'm kind of okay with this, even if it's a cartoonishly naive model, because we do those all the time in control, right?
After the strength of the coupling reduces resistance. Okay.
Yeah, so that can go into your cost function, right? So like in particular, you have these collision constraints, which aren't active until you're really close. You can similarly kind of encode some notion of like following distance kind of stuff in the cost. And like all these can be functions of, distance and kind of reflect that sort of thing, right? The interesting question that leads to is then if I'm trying to if I'm in a partially observed setting, uncertain setting, I don't really know these cost functions for the other drivers. If they are strong functions of distance and stuff, it means I can't observe them unless I'm really close and like kind of getting up in the other driver's business, right? And like following too closely and kind of perturbing them, right? Otherwise, if I'm just sitting there 2 lanes over and they're driving, I can't know anything about this. I can't like really observe their cost parameter. So this gets at like this, I think in a very fundamental way, this is a like, in the online setting, it's a low data scenario. We really can't like do too much online observation of what the other drivers are going to do. So you need a strong prior over this stuff anyway, which again gets back to this model might be cartoonishly naive, but like you can't get that much data online anyway. And maybe it's okay. I don't know. But again, I think there's lots of work to do there. This is very much in the current research flavor. Yeah.
Is there any way to incorporate that the other driver acted in regard to like they do something, even if it's like a slight shift in the direction or in like theory becoming a perfect see no driver.
Yeah. Oh, you're talking about like actually like if I'm looking through the windshield at the other driver kind of stuff, or are you just saying observing the car doing stuff?
Yeah, like if you observe the car, maybe
Yeah.
they, like,
Yep. So that's in here, right? So that basically is assuming we're assuming full state observations here, right? So assuming I have some perception system that's tracking the other cars and I have the full state vector, that's in here, right? And so the idea is online, we're going to try to do this rapid MPC loop around this and resolve it. So let me talk about that for a sec. So we did this. So how we did this. So how we solved this is a paper called All Games that we put out a couple of years ago. And it's augmented Lagrangian Nash game solver on brand for us because everything's an augmented Lagrangian. So the idea is form the augmented Lagrangian for like each player in that player level problem. And this is to handle the constraints. So you take like each one's first order necessary condition. So like we'll get a Lagrangian for player I, and it depends on all these things. And something like this, right? So their cost function. And then you'll have all the constraints in this. You'll have the penalty term. Then you'll have a Lagrange multiplier. That will have, say, the inequalities, right, in the usual way where we take the sort of the violation. So I'll call that C plus. And then like a Lagrange multiplier for those guys. So we're doing this for each of those problems, right? So each player I, we get one of these. So I then remember in the augmented Lagrangian method, I'm just solving this for the primal variables, not the duals. And in particular, right, all I'm doing here in this game theoretic setting is taking the gradient of this thing for player I's controls. So I get this first order necessary condition. I do this for every single one of these. So I get n of them. So stack these conditions. And I'll get, a bunch of these guys that look like, like this sort of thing. Stack them all up. All these set equal to 0. I can solve that thing with Newton's method. So it might not be super obvious, but this ends up being square, like a nice, kind of set of first order necessary conditions. I can do that. Then I can do the standard like outer loop augmented Lagrangian update. To get the lambdas and the mu's. And that's kind of the idea. We were able to, by like, dialing in the implementation of this a bunch and some secret sauce, taking advantage of sparsity, all the usual things we talk about. We got this to run at like between 30 and 50 hertz for like 5-6 cars. Starting to look like pretty reasonable for like what you might do in a real like highway setting where you're just looking at who's around you. And that was without really doing a ton of parallelization. So I'd say like this is quite doable for like a realistic driving scenario if you actually cared and wanted to try doing this. So reasonable rates for like MPC for like a handful of cars. And like, if you actually watch this and like look at what comes out of this, you get like pretty nice human-like interaction strategies. It solves the frozen robot problem that we started out with. It like reasons about nudging and like, other people making space at like on-ramp merges. We did some like zipper merge examples. I don't know, all kinds of weird stuff. The other thing, going back to the models being naive, we also looked at some of that stuff, like robustness to like these assumptions being wrong and stuff. So we've like looked at examples where you have like a pedestrian crossing and it's just doing a random walk and like you have no idea. And basically the MPC, kind of feedback is pretty robust to that. So even if your predictions are pretty wrong, you're resolving constantly and you have these hard no collision constraints. So in terms of like safe, it's pretty safe. So it has these hard don't hit anything collision constraints in it. It's resolving at 50 hertz. It's probably not going to hit anything, even if it, the thing you're trying to not hit doesn't act exactly the way the predictions kind of show, right? All right. And if you're interested, we've got some papers on this. There's a YouTube video from like an RSS talk from a couple of years ago when we published this that has the videos in it. They're pretty cool. You want to check those out. Let's see if I can grab this. There it is. Okay, so yeah, this is like the original thing. So you can see like basically we looked at like this merging scenarios and other kind of things. And then we did a follow on to this that like anything else cool in here. Yeah, I don't know, some weird intersection things, pedestrian things. And then we did a follow on where we tried to actually estimate the other drivers' cost functions online to sort of relax this, prior assumption. And this got really interesting and super, super fun. The main takeaway though is that you really can't like estimate that much online because it's kind of this sparse interaction flavor and you don't really know anything about them until you get pretty close and there's interaction there. But we did all kinds of fun things and like basically, did like multi-prediction kind of rollouts where you have like a belief over their cost parameters. And so you actually like roll out all of those beliefs sort of in parallel and use all of them in your constraints, in your collision constraints and stuff, right? So if you have uncertainty over their cost parameters or whatever, you basically like try them all and you put the collision constraints on all of them. So you're like extra safe, essentially. You're basically being safe with respect to like a reasonable range over those parameters or whatever. And that's kind of what these are showing. Kind of fun. You get like really interesting behaviors out of this, but it's definitely hard and weird. Anyway, that's it.